Hello, everyone. Welcome to the SNIA webcast, the SNIA NSF webcast on everything you want to know, but we're too proud to ask about data reduction. So we will get started. Oh, looks like it is the top of the hour, so we will go ahead and get started. My name is John Kim. I am your host, and our great presenter today is Alex McDonald. So
hi, John.
Let me, oh, Alex, hello. Thank you for joining us today. So, some happy headshots. That's me on the left. I am the chair of the SNIA Networking Storage Forum, which we will call NSF, which does not mean National Science Foundation, but we cover topics of equal importance. And on the right is Alex McDonald, vice chair of the SNIA Networking Storage Forum, and also chairing some other SNIA groups. Alex works for NetApp. First, before we get started, let me talk a little bit about SNIA and then a few housekeeping topics about asking questions and downloading content. So, for example, the content for this webinar will be available for download. In fact, it is available now. If you see below your presenting screen, there should be a tab that says Attachments and Links. And if you click on that, you can download the slides. That's a common question we get. Also, this webcast will be available afterward as a replay, both through BrightTalk, and usually we also put it later on the SNIA YouTube channel. As far as questions, we encourage questions. We ask that you put the questions into the question tab or the question section. You can ask them, and we will answer as many of the questions as we can, either during the webcast or at the end. Any questions that we cannot get to today, we will answer in an FAQ, which is usually published 1 to 2 weeks after the webcast. So let's talk about SNIA. SNIA is a technical organization that focuses on storage, networking, and many topics related to storage. You can find out more about us by visiting SNIA.org and more about the technical aspects at SNIA.org/technical. We have over 185 industry organizations, more than 2,000 active contributors, and more than 50,000 participating members worldwide. Some of the technologies we cover in the Networking Storage Forum, or NSF, are Ethernet, iSCSI, NVMe over Fabrics, InfiniBand, Fiber Channel, and FCOE, hyperconverged infrastructure, and so forth. We also cover different types of storage and different ways of implementing storage and storage networking. Quick legal notice. So the material in this presentation is copyrighted by SNIA unless noted otherwise. Member companies and individual members of SNIA may use this material, but they must attribute where it came from and must use the slides in entirety without modification. This is a SNIA project. Neither the author nor presenter or the moderator, which is me, none of us are attorneys, and so none of this should be construed as legal advice or opinion of counsel. If you need a legal opinion or legal advice, please consult your own attorney. This information represents our personal opinion and current understanding, and we do believe we're quite knowledgeable about storage and the related networking, but we do not warranty or guarantee that this information, do not provide any warranties or guarantees for this information, and you use it at your own risk. Okay, I'll give an introduction and then we'll jump right into it. So just a quick recap, if you're joining late, remember to please ask questions during the presenter-to-presenter chat. You can download the slides. I see several people have already. If you go to the Attachments and Links tab, you can get the slides now. We will answer as many questions as possible live, and any other questions will go into a published FAQ or, I'm sorry, a published blog with all the questions. And if you have any audio problems, usually the best thing is to refresh your BrightTalk screen, and that usually will fix it if you lose your audio connection. Let's see. Alex, are there any other housekeeping issues I forgot before I dive into the agenda?
No, I think you've pointed out where the exits are and how to wear a face mask.
Okay, thank you. And at the end, we do ask that if possible you give us a rating and provide your feedback in addition to the opportunity to download the slides. So, what we promised to cover today, it's it's data reduction, which includes deduplication and other methods. So first, how do companies end up with so many copies of the same data? Why would people make so many copies? Why would you deduplicate if you could just avoid making copies in the first place? Second, what is the difference between deduplication and compression? When should you use one, and when should you use the other? And do you ever need to use both? Where and when can you reduce data? Should you do it at the application or at the storage or during backups? Can you do it in more than one place? What are snapshots? What are clones? What is thin provisioning? What's the difference? How do they work? Can you use more than one method at the same time? And where do they work? Where does each one work the best? And finally, when to collapse the copies or reduce the data? Should I do it real time as the data comes in, or should I do it post-process sometime later? And finally, Alex will look at the performance considerations. So Alex, with that said, let me advance the slide and hand it off to you. Please go ahead.
Thank you. I thought it worthwhile that we actually did what we promised to cover, because I sometimes find when I go on a presentation, the speaker fails to cover what he promised to cover or she promised to cover. But I'm hoping that we do exactly that in this presentation. I just wanted to start to talk about the age of loads of stuff, the age of Aquarius and the age of loads of stuff. My goodness, have we got loads of stuff? Why is there so much data? That really is a question I can't answer, that we seem to be adept at generating it by the ton. I thought I'd go out and take a quick look and do some research and find out, for instance, how many Facebook photographs there were. And I went back to 2008, where Facebook claimed they had 10 billion photographs on their system. In 2014, 6 years later, they had 240 billion, climbing by 340 million photographs a day. And in 2020, I couldn't find any statistics. And I think perhaps that's because actually no one cares anymore, because nobody can actually find out how many photographs there are on Facebook. I don't think Facebook even know. I don't think anyone can count them anymore. And I also did a Google search. I remember when Google first came out, when you did a Google search on Google, you didn't get any hits back because they actually hadn't trawled their own pages. But now if you do a Google search on Google, certainly my Google search returned 9.8 billion page hits with the word Google somewhere inside them. I mean, the amount of data we're generating is just astronomical. And that's just an example. That's just one, if you like, end user example of data creation. But we have other elements of data creation as well that I'll talk about shortly that we can do something about. And we can actually reduce the amount of data that we're keeping. Most companies' growth is obviously a lot less than it is for Facebook or Google. I mean, these are really they're not only just hyperscalers, they're actually hyper everything, hyper growth too. The multi-petabyte data centers or cloud acquisition of data, space rather for the data, with multi-terabyte a day growth is not that uncommon anymore. And even small organizations find that they're progressing through the terabyte into the petabyte range. Just quite simply, the amount of data we have is growing hugely. Now that also leads on to the point that data generates data, because as soon as I put up a photograph or a video or a virtual machine or a container or a PowerPoint presentation or whatever it might be, I've created the data and then I copy it somewhere else to process it or present it or to play it. And then I back it up, and I possibly back that back up too. And then I make a copy again to process it somewhere else for a fourth, third time, second time. I can change it, if only, and I've tried to give an example here, changing something very slightly. I corrected a spelling mistake I made and simply changed it from the incorrect word to the correct word. And that generates yet another PowerPoint presentation that's not quite the same as the previous PowerPoint presentation. But as we'll see, we can deal with some of this and actually reduce the amount of data that we're storing, and also try at the final analysis to actually understand that the per bit cost is reducing. The number of bits we're storing is growing faster than the reduction in the per bit cost. Do I have proof of that? Well, I could probably go out and do a bit of research. Perhaps I should have done. But that's an anecdote. That's anecdotally. I believe the case that this is fairly self-evident, that the amount of data that we're generating is growing far faster than the cost of storing those bits is decreasing. And that's quite a worry.
Alex,
the other thing
is that we're
yep.
Oh, it strikes me that we're trying to help this trend along here as we prepared this presentation, because we came up with, let's say, 5 versions of this slide deck which are very similar, and then let's say if you emailed it to me, then you have a copy on your
yep.
computer, in your email. I have a copy in my email. I downloaded a copy to my computer, and then of course my computer gets backed up to the cloud, and then we posted it here in Bright Talk, and we encourage everyone to download a copy. So I think we're helping this trend along of creating similar or identical copies of the same slides.
Yeah, we did. In fact, the other thing we also managed to do in this presentation, about an hour before it was put up on the website ready for presenting today, was to duplicate a slide in its entirety. Slide 16 and 17 were exactly the same. So we've done a certain amount of data reduction by getting rid of that duplication, but correspondingly, we've created yet another presentation. The other thing that's quite interesting to note is it's difficult to delete data, and in fact, modern deletion techniques aren't about deleting the data itself, but by having keys that allow us to decrypt the data. We encrypt the data with a key, and if we throw away the key, then we don't need to delete the data because it's become instantly unreadable because we no longer have the key with which to decrypt it. And that leaves a lot of data lying around that is actually deleted in the sense I can't read it anymore, but not deleted in the sense that I'm still storing it. And that's a big problem. And that is becoming an increasing issue, actually. So how can we reduce the impact of all these things that we find it difficult not to do? These are all sensible things to do, but like bacteria, one bacteria turns into 10, turns into 1,000, turns into 1,000,000 in fairly short order, and they're all identical, or they're identical apart from a couple of mutants that then start multiplying. So we've got this issue of an awful lot of data, and we need to do something about it. So data reduction is very much a thing we want to do. And today I'm going to talk about the common techniques of doing data reduction. Some of them you may have heard of before, some of you may be very aware of, and some may be a little novel, and you may be thinking, oh, I didn't know that could be considered a data reduction technique, but here we are anyway. We've got deduplication, which is removing duplicate stuff from the data. If you think of those 2 PowerPoint presentations, if they're absolutely identical and we store them somewhere we can recognize that they are identical, then only store 1 copy and point to it twice. We can remove sparse data. In other words, there may be data out there in our data sets, things like databases, for instance, that contain lots and lots of repetitive bit patterns, probably 0, sometimes not, but these can be deduplicated or removed, and instead of pointing at or storing large numbers of blocks of data that contain nothing but infinite strings of zeros, we can simply not store them at all and simply point to where they should have been and say, anytime I'm reading in this area, then return zeros, because that's exactly what I suppressed reading in the first place. So that's deduplication. Compression is about squeezing the data into a smaller space. And we'll take a look at some compression techniques and how we can do compression and really reduce the amount of data that we're having to store once we've decided that we can compress that data. Compaction is another technique. Compaction says the things we're storing in, if you think of like cookie jars, if you've got a dozen cookie jars with only 1 cookie each in them, that's pretty inefficient. All that space is being wasted. Each cookie jar could store far more cookies. So why not move all the cookies in 1 jar and suddenly I've got 11 empty jars? So compaction is all about simply filling the space up or packing the space up far more efficiently than we might do otherwise. Snaps and clones, I'll discuss what they are. Snaps and clones are about providing you with what looks like unique objects that are in fact replicated objects, objects that share in common parts of their data with other objects. And I'll cover snaps and clones in a second. And then thin provisioning and hole punching. Thin provisioning is about appearing smaller and recovering space. And that's exactly what hole punching is about as well. If we've got a hole in a data set, then don't store the hole. Return that hole to the free space pool. And again, I'll cover that. The interesting thing about these techniques is that they can be applied to all storage types. So if you think of storage types at a fairly high level as being things like files, as PowerPoint presentations, PDFs, text files, etc. Block-based, that's things that databases usually live on. In other words, 4K blocks of data, or certainly some round magic number that's 2 to the power something, sets of data that we can address block by block by block, or objects, which are just basically big binary blobs that start somewhere here and then somewhere over there. These kind of things can all be subject to data reduction techniques. There's no reason that we need to think differently about files from blocks, from objects. The same techniques can be applied to all of them, although the technique itself might differ. We can compress them all, but we might use different types of compression depending on what we're actually looking at and storing. So let's cover some of these. Let's go through some of these. Before we do that, though, we need
Alex, you have to use the analogy of the cookies in the cookie jar, and the first thing that came to mind for me is if I were faced with that problem, I would just go to 6 of the jars, eat the cookie, and then I have 6 empty jars. But I don't know if that actually works for actual data, because you probably don't want to just go eat the data as a way to save space. So anyway,
I'd also like to point out, John,
that
you're far slimmer than a man who might eat 6 cookies in a single sitting. So I don't think that's actually really true. That's more likely to be me, to be quite honest. So one thing that please go on. Yeah, cookies aside, one thing we have to recognize about all this is that much like virtualizing if you think of virtual memory, whereby we address memory in our laptops, and what appears to be byte address 1024 isn't in fact, it's somewhere it is being mapped to another address, the real address. So the virtual addresses and the real addresses are not necessarily the same thing in virtual memory. We need to do that with storage as well. We need to virtualize our storage. It's a prerequisite to doing a lot of these techniques. And the reason for that is that, in general, we need to be able to carry metadata along with the data. And we need to make that seamless and transparent, and to make sure that it's there when we need it, but it doesn't actually get in the way of what we're trying to do. And I'll explain what a virtualized storage system looks like. The other thing is, I'm going to be talking about not a specific type of storage system. Now, there are many vendors of virtualized storage, but I'm not going to be talking about a specific implementation. This is a generalized implementation. Don't assume that all systems work the same way. They don't. There are a variety of ways of doing this. These are simply examples of some mythical system that I invented to be able to demonstrate some of these points. Excuse me. So we're going to review some of the commonest techniques. It's not an exhaustive, and it's not authoritative either. The performance varies between the solutions, and I will try and address some of the performance issues when we get to the back end of the presentation. For specific techniques, ask your vendor. Your vendor is the font of all knowledge when it comes to how they implement some of these features. So ask them how they're implemented if you're interested. But at the end of the day, how it's implemented, I think, is not that important. What is important is that you can do serious data reduction and that you have some handle on the kind of data reduction you can do so you can buy the right amount of space in the first place. So in general, we require a virtualized storage system. Data reduction technologies generate metadata. That's data that describes data. And the one-to-one relationship between the data and the layout on the physical device is completely lost. And we're going to use this simplified conceptual model. So, what does the physical layout look like? Well, the answer is really, well, who cares, to be quite frank. At the device level, everything's based on blocks or sectors or clusters or pages. SSDs are different from disks. We could have tape. It really doesn't matter. That's detailed knowledge that we really aren't interested in. It's too low a level for us. We're not really interested in managing or providing a virtualized storage system at that level. So this detailed driver knowledge is really one or perhaps even 2 layers of technology further down the stack than we're going to be discussing today. The overall model I'm going to be presenting with is relatively device independent, as long as the device supports random access. Because as you'll see, it depends on having blocks and pointers to blocks. So
Alex,
the detail
that if we talk about, for example, deduplicating blocks or something that are we doing that at the physical blocks on the storage device, like in the SSD or hard drive, or is it logical blocks in the file system, or is the answer it depends?
The answer is it depends. So, for instance, I'm going to be talking about this virtualized storage system, and we're going to talk about blocks. And they may actually be physical blocks on the device, but at the end of the day, they may not be. They may be abstracted away. It depends very much on the vendor. It depends on the device. It depends on what kind of software technologies you're going to be using on that data to be able to do this data reduction. So the answer is fairly woolly. The answer is maybe, perhaps. But certainly one thing I'm not going to talk about today is how these devices work, because that's just too low a level. What I am going to talk about is this conceptual virtual model. It's almost like a pseudo file system that virtualizes blocks of storage. So these are not real blocks. They may be real blocks, but they're not necessarily real blocks. But what we have is a structure of pointers and data, and the pointers point to the data. And at the top level, we have these things called inodes, or indirection nodes, which are metadata that store information about the data itself. And it looks like a file system. And in fact, the picture on the right is a file system called ext4, which Linux people will know. And that is very much the conceptual model you'd have for an ext4 file system. So there are file systems that look like this. There are also systems that manage block devices that look like this, because these blocks are basically blocks. So we could actually treat this as a block device or a file device or even objects. What's to stop these things being objects or parts of objects? Absolutely nothing. But the mapping is done by layers below the virtualization level. We're not really interested in it. What we do have on the right-hand side, though, is an inode, the major node, that's pointing either directly to the data, or you can have levels of indirection. So I've shown here an indirect data blocks, where we can obviously have inodes pointing to inodes, and that allows us to have a larger number of blocks that we can manage in a single entity. Or we can have double indirect, or even triple indirection. We've got inodes pointing to inodes pointing to inodes that eventually point to the data blocks. And I'll use this as a model for actually demonstrating how we do data reduction. So that mapping, these inodes, is all managed at a higher level than what we're doing on the device itself. We're not really interested in the device. This conceptual virtual model will serve us well when it comes to doing data reduction. So the techniques, and I've already covered them: deduplication, compression, compaction, snaps and clones, thin provisioning, and hole punching, and we're going to discuss it in terms of that virtual model. So let's start with deduplication. The general principle of deduplication is really simple. Don't write data you've seen before. And it's an easy thing to say, but it's a hard thing to do. This can work with files, blocks, or objects. And I'll give you an example of not writing something you've seen before. Let's say we have a PowerPoint file that I copy on my hard drive and copy somewhere else. Well, if I could deduplicate that, I just simply need to point to it twice. It might have a different name. It might be, copy 1, the first copy, and copy 2, the second copy. But if it's identical, then why store it twice? Why not just point copy 1 and copy 2 at the same file? So I can deduplicate files that way. I can deduplicate blocks. So if you think of block storage, 4K blocks, and I can go and inspect the blocks and look at them and say, have I seen this block before? And if the answer is yes, then instead of writing the block, I simply point at the block, because I already got a block that's exactly the same, and I can have multiple pointers pointing to the same block, and that block is being shared among several different parts of my data structure. And the same is true of objects. So I can deduplicate objects the same way, either the whole object or part of the object. I can slice the object into pieces and deduplicate that. But the idea is that if you look at the diagram, we've got the before and we reduce it to the after. Now, most of these techniques of deduplication require knowledge of, have I seen this before? Have I seen this thing before? And we use a query that returns a value that says, I have definitely not seen this before, in which case you need to write it, or I've possibly seen this before, but you need to check, because I might be wrong. And that may sound a bit sloppy. Why don't we know that we have or haven't written this block? And the answer is quite simple. If we had to check every block to see whether we'd written it before or not, that would require humongous passes through the data. And that's just not on. We can't do that. So we use a simpler technique than that. Instead of trying to work out whether we've seen this particular block by comparing its bit pattern with every other block we've written. What we do is we actually use some technique that allows us to say we have possibly deduplicated or definitely not deduplicated this block and act appropriately. And we can do that with little functions like hashes or Bloom filters or cuckoo filters, I'll cover those in a second, that allow you to do that. And the one thing you need to recognize, though, the bigger the deduplication space, so in other words, if I'm deduplicating a single disk, then that's a fairly large space, but it's a lot less than deduplicating an entire SAN, or it's a lot less than deduplicating an entire cloud. So deduplication doesn't normally take place over extremely large spaces. It takes place over relatively smaller spaces, but the benefits of doing so can still be considerable. So just let me cover how these work. And I'll give you an example here. So we can use either Bloom filters or cuckoo filters, or there's the variety of them, XOR filters. There are even ones called Bloomia filters, which I think were Bloom filters with extra bloom. I'm going to give an example of a simple hash. Let's say that I take a 4K block of data and I hash it. Now, a hash is simply a function that returns us a number that represents the bits in that block. And that number can be very small. And I'm going to use a 16-bit hash, or 2 bytes worth of data to illustrate the issue. So I hash that block up, that 4K block up, and then I use that 2 bytes as an index, because it's a number. It's a 2-byte number. It's a 16-bit number. And I can use it as an index into a table that says, have I seen this block before or not? And if I have seen it, where did I put the block originally? And at that point, I can either get back, oh, I haven't seen this block before, in which case I definitely need to write it, or perhaps I've seen it before, and I've got this block point, and I go and read the block that I'd saved before that matches the same hash to make sure it is an identical block. And if it isn't, I write it. If it is, then I simply point to it, and I don't need to write it. So these hash functions, these simple hash functions, need metadata space. And they're very, very powerful, however, in identifying whether the block is a member of the set that we have written or we haven't written. And it's this idea that we can do really simple things to identify whether the block has been written already or not, and consequently deduplicated. We can also do things like common pattern elimination. We can reduce, not write 0 blocks. That's really commonly done. Detect the block is full of zeros, don't write it. Simply point at or say in the pointer to the block, this is in fact a 0 block, so anytime you're asked for this block, just return all zeros. We can do it with patterns. Some databases use block patterns to indicate free space, notably things like Oracle. And for them, what we can do is simply not write the free space blocks. And anytime somebody asks for that particular block, we simply return the bit pattern that we suppressed. And that's a fairly common technique to use. Excuse me a second. Glass of water. A little cough there. So, all we're now doing when we deduplicate the data is we're taking stuff that we've seen before and pointing at the stuff we've already written. And if we've not seen it before, we write it. So deduplication is a really simple and elegant way of reducing the amount of data that we store. And you can get quite effective deduplication rates. Some data deduplicates incredibly well. I'll give you an example. VMs, virtual machines. If I have 200, 400, 1,000 desktop machines, the number of blocks that are in common between each of those desktop machines is very high indeed. Perhaps as much as 90% of each VM is exactly the same from VM to VM to VM. And I don't need to store all those blocks. I just store one copy and point the 999 other copies of that block at this block that I've written. So you can reduce the amount of space you require quite dramatically with these simple deduplication techniques. Is this the only way of doing it? No, there are lots of other ways of doing it. But that's the fundamentals of deduplication. Don't write something you've already seen before.
Alex,
so here's
oh, actually, sorry, go on, finish this, and then I have a question related going back to the cookies, but please go on.
Okay, that's fine. So in this example, what I've done here is I've deduplicated the data. I've got the same data, but very much less space, because block A and block E, I saw block A before, so I simply point at it twice. And I've seen block E before as well. So I've reduced the amount of data. So instead of 1, 2, 3, 4, 5 blocks, sorry, I've only written 5 blocks instead of 7 blocks. I don't have 2 copies of A, and I don't have 2 copies of E either. So I've reduced the amount of space I require by quite a bit. Go ahead, John.
Oh, well, I'm still obsessed with this idea of cookies and cookie jars. So you're telling me that, let's say I had a bunch of cookie jars, and a lot of them just had, the same one cookie, and many of the cookies are identical, but I have, oatmeal cookies, chocolate chip cookies, sugar cookies. So you're saying that first I could deduplicate by, instead of having, 50 oatmeal cookies, I could have just one, but I could have metadata that points to the same cookie 50 times. And then if I have at a higher level, if I have a bunch of jars of cookies, and those jars are identical, I could just eliminate some of those jars and have metadata that points to the jar and say, oh, I have 8 copies of this jar, but I only keep one.
Which is exactly how an Amazon warehouse works.
Okay.
If you think about it.
And then if I have cookies that are cookies are like VMs, if I have a bunch of cookies that are 99% the same inside, I could even store only store the unique parts of each cookie, and the rest of the cookie I can just keep one copy. So I see this as a tremendous savings, but from a cookie standpoint, I get rather sad about it, because it means that I thought I had hundreds of cookies. Now I just have like 3 or 4 and lots of metadata, but I can't eat the metadata.
Yeah, so that's very true. And also the other thing is, some of the cookies, like the all zero cookies, don't really exist. There's just a recipe for them. And we know when we go look for an all zero cookie that the recipe says just return zeros. There's no real cookie there.
So you don't even
take the cookies too far, though.
If it's a zero cookie, you don't even keep it. Yeah.
Exactly.
Okay.
So just to come back to this diagram very quickly, we've reduced from 7 to 5 the number of blocks we need to keep. We have, however, increased the metadata. There is metadata required for all this. We've got pointers to maintain, but it's a lot less. The pointers are a lot smaller than the actual underlying data. And so the reductions can be quite considerable with deduplication. So moving on from deduplication, we've got compression. We can compress the data. Now, there are 2 types, or primarily 2 types of compression, lossy versus lossless. Now, lossy compression is the type of compression done in things like JPEGs, where compressing the data and not being able to recover the exact bit pattern is okay, because we can recover something that's nearly what the bit pattern was, and that's fine, because our photographs don't need to be that high resolution when we're, for instance, making thumbnails out of them. So lossy compression is fairly common, where you're not concerned about individual bits. But in storage systems, in general, we are concerned about individual bits. And one of the nice things about a storage system is, if I give you a bit today and tell you it's a 1, when I come back in 20 years' time, you'll give me the same bit back and tell me that it's still a 1. And that's important. So we don't use lossy generally. We use lossless compression for pretty obvious reasons. We don't want to destroy your data in the process. The thing to note about compression is, although compression can be really good and you get some really aggressive compression rates, high compression ratios are very high overheads. And we tend to use fast and simple compression techniques for inline compression. That is, compression carried out now as we're writing the data. It is possible to carry out compression later, and I'll talk about when these things are done a bit later in the presentation. But high compression ratios tend to have high overheads. The other thing to note is, already compressed data generally compresses badly. And in fact, if you've ever tried it, take a zip file that's compressed and compress a zip file. And in general, all you end up with when you compress a zip file with zip is it puts the zip file inside another file, but it doesn't attempt to do the compression. It's made the file a bit bigger because it's added headers to say the contents of this file is simply a zip file. But at the end of the day, compressing compressed data is a serious waste of effort. And because it usually inflates the data, what happens when we compress it, and I'll show you an example of this, is that we don't use the compressed data. So we attempt to compress the data, and if it fails to compress to a reasonable degree, and that degree depends on the storage system, might be 25%, might be 50%. If it won't compress more than that, then we simply throw it away and we use the uncompressed block, because the effort of actually compressing it is completely wasted, and decompression costs money, because you have to read data that's being compressed, you have to decompress it, and that also costs effort and overhead. The question I often get asked is, should we compress or then deduplicate, or should we deduplicate then compress? And the answer is, there's not really much of a difference. But in general, what I see is that most systems compress, then deduplicate. And as the diagram on the left shows, you've got the uncompressed data, you squish it up, and then you dedupe the stuff that you've squished up. We'll talk about how we go about compressing data and making sure we can still address it in a second. But in general, we use lossless compression, high compression ratios of high overheads. If we can't compress satisfactorily, then we just use the original block, because it saves us decompressing something where we had a very small or marginal overhead in terms of space saving. And normally, you compress, then deduplicate the data as shown in the diagram.
What happens if you deduplicate first and then you try to compress, or should that be, is that getting too much into the weeds, and we should cover that in a future webcast?
That's possibly too much into the weeds at the moment, but in general, there's not a great deal of, it depends on the data. There's not a great deal of difference whether you deduplicate then compress, or compress then deduplicate. There is a big difference, though, when it comes to actually writing to the physical devices. So there's normally a trade-off to be made here, and for performance reasons, compression and then deduplication is to be preferred. But we can cover that in detail in the next presentation. So here's an example compression process. So read the notes first of all. I'll explain the diagram in a second. The blocks are broken into compression groups. So we don't compress the entire thing. We compress parts of the data. So we take let's say a big database, and we actually just simply compress it in chunks. And there's a reason for that. And the reason is really simple. We need to be able to read the data without decompressing huge amounts of it. And if we compress the entire thing, then we'd have to read the entire thing and decompress it before we could address a part of it. And so to stop us from having to do that every time, we use compression groups, which are just smaller blocks of data that we compress and place on disk, so that when we're reading something from that group, we simply decompress that group and not the entire thing. If we can't compress, then we don't compress, or if there isn't a satisfactory return on the compression, because, as I say, decompression costs money, so we just use the original blocks. And if you look at the diagram, I know it's rather small, but you may be able to make this bigger on your screen. You can expand the presentation to full screen. You'll be able to see, and I'm going to try and read this along with you. Just bear with me a second while I pick up the original. You should be able to see what you've got is stripe 1, or column, sorry, I beg your pardon, row 1, it writes from the hosts and client. Basically what we've got there is data with varying degrees of compressibility spread across 3 volumes in this case. So we've actually got this pseudo file system describing 3 volumes, volume A, B, and C, and 50% to 80% compression on volume A, volume B, 50%, and then volume C looks like it just doesn't really want to play. It's very small bits, 3 small 1K segments. So what we do with, first of all, is that without compression, we'd obviously have to lay the data down in just basically one block after another, big long stripe of the stuff. So we'd end up with 11 blocks in total to write that data from the hosts, from the clients, I beg your pardon. However, if we compress it, the stuff in pink compresses well, so let's compress it out. The stuff in blue doesn't compress, so let's just use the original. And we end up with 8 blocks as opposed to 11. So compression has actually saved us some space, and we've only got a small amount of overhead in decompressing for some of the data, because we didn't compress stuff that really wasn't that compressible, and hence we haven't needed to deduplicate it. So that's how compression works. And again, this is the kind of technique that some systems use. Other systems may use other techniques. For file-based compression, obviously, if this was a true file system, then we could compress the entire file, because there's actually, unless you've got very, very large PowerPoints, compressing the entire thing is okay, because decompressing the whole thing is normally what you do when you pick up a PowerPoint presentation. So file-level compression generally takes place at the file level. The block-level compression, objects based on block systems like databases, and this is in fact an example, I think, of a MongoDB database, tend to use block-based storage, and they will do their compression at the block level. So that was compression. Have we got time for a quick one? Why does video do dedupe before compression if the other way is preferable? It isn't preferable. It depends on the data, and that's an example of where one technique, that is dedupe before compression, is preferable to compression before dedupe. And I can't answer the specifics of that. I'm not 100% sure of what is going on under the covers there, but it depends on the vendor which way around is done. Compaction is filling in the gaps. So if you remember that diagram on the previous slide, compaction is all about simply taking data in blocks and putting it into a single block. And obviously what happens is the inodes, remember the metadata, just points off the various parts of a block rather than the entire block. So instead of pointing at the beginning of the block, it points into the middle of the block, if that's where we ended up putting this small segment of data. And if you go back to our original, where we actually compressed some of the data, if you look at the after data compaction, we've done quite a bit of compaction. And in fact, that data has gone down from 8 blocks to 4 blocks. And in particular, volume C has gone down from using 3 1K pieces that meant 3 4K blocks, all the one down to 1 4K block with only a slack, if you like, of 1K at the back end. So there's lots of techniques for actually doing compaction as well. You can actually fit many small objects into the larger unit that we're dealing with at the virtual file system level, where we're actually dealing with blocks of data. So that's compaction. So another technique that we can use. And then perhaps the one that most people are now familiar with, snapshots and clones. A snapshot I'm going to define as a static copy, unchangeable, read-only. And a clone is modifiable. So a clone is actually just simply a copy that you can modify. And they can provide significant data reduction, because you can see the first example up here. We've got 4 blocks of A, B, C, and D. We take a snapshot of it. So we've got the original pointing to A, B, C, and D, and the clone is now pointing to A, B, C, and D. But we can go and update the clone, and hey presto, if we update block C, all we need to do is write the modified block C, and point at it. The original remains undisturbed. So only the updates, only the deltas, only the changes are being accounted for. And if you think of the way that backups work, this is classic backup territory, whereby I am only storing the changes. I take a base level backup of all the data, and then on a daily basis, or however often I do backups, I take a delta of that data. What's changed? It's only the change data that I'm going to store, and that's been done for backups since since Moses came off Mount Sinai with the tablets. It's a technique that we fully understand. So snapshots and clones are also great space savers.
Alex, is it accurate to say snapshots and clones, and maybe I should have waited till you finished this slide, but the snapshots and clones only can save space within the same storage system? That is, you can't use it to save space across different systems or different data centers, right? Or have I got that right?
You've got that right. In general, although there may be specific examples where that's not true, because you can actually have the clone the modified blocks off in another system, but we won't go into that because that's too detailed. But in general, you're right. It's only on one system that would be of benefit. You're not going to see a benefit at all across multiple systems. It's only within one system. So the other techniques that we can use, last but not least, thin provisioning and hole punching. Thin provisioning is a really simple concept. If I allocate 2 terabytes, but I fail to write to them, why should I reserve 2 terabytes of real storage for you when you actually haven't written a single solitary bit to it? And the answer is, well, don't in that case. Just thin provision everything. In other words, don't store the free space. Don't allocate blocks to free space. And if you think about a virtual file system, that's a relatively easy thing to do. I have a big inode, but I don't point to anything. All the pointers are empty, in effect. They're pointing to space that hasn't been written to yet. The other corresponding part of thin provisioning is hole punching, where if I delete parts, this particularly applies to things like block-based objects and also file systems like NFS, where you can punch a hole in a data set or a file. You can return that space to the free space pool, and you can actually hole punch these things out. Alternatively, you can use it for compaction space. So you could actually use the holes in that file to compact other smaller files into, should you so wish. Because these virtualized file systems just use pointers to blocks, all these kind of things are eminently possible. So thin provisioning and hole punching, again, 2 techniques you can use to reduce the amount of data that you need to store. So, timing and scope, the when and where. When and where are these things done? So the timing applies to deduplication, compression, and compaction. Those are the first 3 techniques we talked about. Remember, deduplication, don't write what you've already seen. Compression, squish it smaller. Compaction, move small things into bigger boxes. So you can do the reduction in line or out of line. You can either do them now, as the data is coming in, or you can post-process it. So you can actually write the data anyway, and then go and do those things after the event. Inline has some advantages, because you don't actually need very much space, because you're actually doing the data reduction before you need to write the data. But you need horsepower. You need CPU or FPGA or ASIC processing to do things like deduplication and compression. And that can be expensive depending on the kind of data. And it also increases the latency potentially, although really aggressive caching, in other words, storing the blocks in really fast memory, can really help here. So inline can have advantages in that you don't need the space. It also means that you can do aggressive caching if that's your thing. But post-processing, got some advantages and disadvantages, requires more space until the reduction is performed. And it also increases the I/O activity to read and write the data, because not only do I have to write it, but I also have to read it to process it, to do the deduplication, compression, or compaction, and then I have to write it back again. And again, aggressive caching can help here. There are pros and cons to both methods, and it depends which one is most appropriate for the kind of storage you're looking at and the kind of data you're dealing with. There are also static techniques that don't cost you anything in terms of timing, I/O time, and that's things like thin provisioning. Thin provisioning doesn't cost you any extra I/O. It's just a case of, it's not there 1 minute and it is there when you write it, so there's no I/O implications. Scope also applies to deduplication. So those are the timing issues. Scope is how broadly do I do things. And deduplication is one of those techniques that can be done locally. In other words, it can be done on a small set of data. And you're not going to get as much return from a small set of data as you are from a much bigger set of data. But the much bigger set of data, although it effectively increases your opportunities for deduplication, is more expensive, because I need to maintain more metadata the more deduplication I do. And in fact, across systems, deduplication is normally done post-processed. In other words, I go and look for duplicates between one system and another system after the event, because doing so during the I/O is far too expensive to do. So there's, the scope for inline and out of line There's a timing for inline and out of line in terms of the performance benefits and in terms of the cost benefits. And again, I'll come to that in a second about what you ought to do about this. So where are all these techniques done? I've talked primarily about storage, but if you think about it, you can do all this on the host, i.e. you can compress files on your laptop. That's a cheap way of, and in fact, Windows, for instance, offers whole disk compression, not just file compression, but whole disk compression. So you can compress data on your laptop. You can do it at the application level. Some applications are pretty smart about doing things like, I'm not writing this block because I know it contains absolutely nothing of interest, so I shan't write it. You can do it at the file system level, so NAS devices. Those are network attached storage, things that deal with files. NFS and SMB both offer hole punching and zero block and also pattern block suppression, so they can use those techniques. You can do it on storage system controllers. The storage system controller sees all the I/O, and we can make global decisions about all the I/O that comes through, not just the I/O from the particular application or stream. And it can do deduplication, compression, compaction at the block level. Remember, they don't normally do it at the file level because they don't understand files, but they do understand blocks. You can do it on the device, computational storage, which is something we have presentations on coming up very shortly within SNIA. Those are smart devices that can look like standard block devices, but do all sorts of smart things like compress and deduplicate and compact locally on the device itself without you really having to worry about it. The device itself is doing all this for you. You can do it in the cloud, and there are ways of doing snapshots and clones in the cloud. There are ways of, and cloud providers, because they really don't, they want to be able to charge you for stuff and then not really have to store it if they can possibly help it. So they use a lot of deduplication and compaction techniques that you should be completely unaware of as a consumer, but it does happen. And you can get it done on the network, so you can do packet and session-based compression. And you can do all of the above. One of the interesting things here is making sure that you do the things like compression at the right place, because doing compression is a relatively expensive exercise, and it doesn't seem sensible to compress, transmit to a device that then attempts to recompress the data. It may actually, not compress the data, but then when it's actually sent back out over the wire, if it did compress the data, then it has to decompress it to send it back over the wire, which then does the compression on the network cards to reduce the amount of data that's being transmitted, which then does decompression at the other end, and blah, blah, blah. It said, well, lesser fleas to bite them. So you need to make sure that when you're doing particularly things like compression, that you're doing it most effectively and in the right place. And that's not a simple case of doing it everywhere. You need to be quite specific about where you do it. What savings should I expect? Well, hey, it depends on the data. But I've seen people, and companies, storage companies will make guarantees about ratios of size 3 to 1 or even higher for certain types of data. Some data deduplicates well. So databases with large amounts of free space deduplicate. Virtual machines deduplicate really well. Containers, Kubernetes containers deduplicate really well. Some data compresses well, others doesn't. So data that does not compress well is already compressed data. And there are quite a number of sources of already compressed data that just doesn't decompress at all. Some data doesn't compact. In the main, very small files, and it's at the file level we tend to do this, compact really well. And fragments caused by compression are also candidates for compaction. So that, there's mileage there as well. But some of it compacts well, others it doesn't. And last but not least, please ask vendors. Vendors have different techniques for doing all this kind of stuff and will make different recommendations. They have experience and they collect large amounts of information from customers about deduplication and about compression, and they can best advise you on your data needs and on your specific requirements for the kind of data you intend storing on the system as to what's best.
Okay, Alex, just letting you know, we do have 3 questions, but please go on.
I will try and answer them shortly, but really quickly, effect on performance. Again, ask vendors. So there are negatives. There's a trade-off between processing power and space. That's a trade-off that you're going to have to make. But the processing power should always be adequate for the kind of storage solution you're looking for. CPU warheads, things like compression may add latency, may be expensive to prohibitive, depending on how much data you're firing on a storage system. You may have to consider things like cache sizes, because caching is important when you're doing deduplication and compression. The positives, though, are very obvious. If you're storing less data, you're doing less I/O. Hurrah! Who doesn't like that? And that can reduce considerably the performance of a system, just reducing the I/O. And the space savings may also be substantial. Disk space, and particularly SSD space, is not cheap. So on balance, lots of techniques, lots of refinements, plenty of industry experience, and systems that support these kind of data reduction techniques are widely available. These are not anything more nowadays than table stakes. They are not unique to any particular system. You should see this widely available in many storage systems. So that's what we promised to cover. I'm just going to really quickly, have we got enough time, John, to do a minute of questions? I think we do, so really quickly. Does block level compression have any direct advantage over file level compression? Not really. It depends. Maybe. It depends on the data. So if you've got, if it's all files you're storing, then perhaps file level compression is more useful. Certainly file level deduplication may be more useful than block level. Will migration to SSD zoning versus HDD-based blocks and pages impact data compression? Again, not really, because all the data compression techniques work with virtual file systems, and we can control the size of the thing that we're deduplicating and compressing. They don't necessarily need to be 4K blocks. They can be variable length, they can be objects, they can be any number of things. So no, that should not have an effect. What will have an effect is when software designers decide to implement these techniques on those kind of devices, then there may be benefits and downsides to those specific device technologies. The rest of the questions I think I'm going to leave, because we can cover those on the blog. In the meanwhile, I'll hand back over to John so he can finish off this presentation today.
Alex, thank you very much. Great material. So what we promised to cover today, and what we did cover with Alex's great slides here, is how do companies end up with so many copies of the data, whether it's PowerPoint slides or cookies or videos or email attachments. What is the difference between deduplication and compression? When should you use one or the other? Where and when can you reduce data? Do you do it at the application, the storage, the backups, or some combination? You might want to dedupe or do data reduction at the storage, and then as it gets copied to the backup site or backup in the cloud, the cloud could also do data reduction on that same data. What are snapshots? What are clones? What are thin provisioning? And Alex explained how they can help and at a high level how they work. And then when should you collapse the copies? Do you do it in real time or post-process? And the pros and cons. Real time usually requires more work, but means you need less space. Post-process means you're not on such a tight schedule. You can do it when you have the CPU power available, but it requires more space because you store the raw data initially, and then you deduplicate or compress or compress it later. And then you look at the performance considerations. So I'd like to remind you that, as we look at the summary slide, that you can download these slides here. We do love to have you give feedback as well as ratings. So tell us what you thought about this webcast. And you can watch this. This replay will be available both through Bright Talk and on the SNIA, later on the SNIA YouTube channel. And then I want to point out that we have some other great presentations in the similar vein in the series, Everything You Want to Know About Storage, but We're Too Proud to Ask. We have them about storage basics. Some of them are listed here: buffers, queues, and caches, storage controllers, memory, etc. So feel free to take a look in the SNIA NSF webcast library or the SNIA educational library. You can find these webcasts and more. And you can also find many of them on the SNIA YouTube channel. All right. So as I mentioned, please give us a rating, give us your feedback. The slides are available here in BrightTalk right now in the attachments and links section, or they'll also be available from the SNIA Educational Library alongside a replay of this webcast. Alex answered many of the questions, but some of them we didn't get to. We will publish the questions and answers in a blog. And finally, you can follow us on Twitter at @SNIA-NSF. So with that said, I would like to give a big thank you to all of you for attending and a big thank you to Alex for presenting. And I think with Alex, unless there's anything else, we'll wrap this webcast.
No, thank you, John.
All right, thank you. And that is the end of today's webcast on the basics of data reduction.